All right, we're back here continuing to talk about pipes and water distribution systems. And in this video, I want to talk about analyzing a pipe junction. And so whenever we have two or more pipes that converge at a junction, a mass balance is going to dictate that the flow in equals flow out. So, for example, we're going to get to working this in a minute. Here we have three pipes. They're connected at a junction here, and we're going to have some flow that's going in and some that's going out, and we have to make sure that we have a conservation of mass at that point. Okay, and so the other thing that we know about each of the pipes in this example is that the head at the junction for all pipes must be the same. So again, thinking about three pipes that are connected together at a junction, whichever pipe we look at, the head at this point is going to be the same for any of those pipes. So the head loss across the pipe, head loss is something that happens across the pipe, head is something that happens at a junction, at a node. So there's going to be a head here in this kind of problem that we don't know necessarily. If we know the head at the other end of the pipe, though, we can get the head loss. So the head losses don't have to be the same, but the head at that junction does need to be the same for whichever pipe you're analyzing. So this three reservoir problem that I showed you below is commonly used to try to understand this idea. And so each of the pipes is governed by the Darcy-Weisbach equation, which we can write this way if we want to calculate the flow as a function of the head loss, assuming we know the friction factor. And then these other things are values that we probably would know if we were analyzing a specific system where we were like, what's going to happen here for these three pipes where we know their diameter and length, but we don't necessarily know what their head loss is, their friction factors, or their flow rates. So this problem is, again, very helpful to try to understand how to analyze junctions when you're looking at water distribution systems. So we're going to work through it, and that will hopefully help when we talk about an actual distribution system in the next video. So the procedure that we're going to use to analyze this three reservoir problem is we're going to pick a head at the junction. So again, our kind of key unknown for this problem, and the other problems we worked in the last couple of videos, the unknown that we really needed was the flow rate. Here, our key unknown is going to be our head at the junction. Once we get the head at the junction, then everything else is going to follow from that, and then we can set up a closure condition, again, that we can use to solve this kind of problem. So the procedure we're going to follow is to pick the head at the junction. We're going to guess something. We're going to then find the delta H for each pipe. So, in this problem with the three reservoirs, this isn't something you're going to see in the real world. Nobody would construct three reservoirs connected together like this, but this is the right way to understand how to analyze junctions. So that's what I want to emphasize to you. But so if we know what the head is at this point, then the head loss is just going to be the difference between the height here, because all the head here is an elevation. There's no pressure at the top and there's no velocity. Likewise, for this reservoir, the elevation here is going to represent the total amount of head. Here at the junction, we have some elevation head, and then we're also going to have pressure because it's confined. But so anyway, the head loss is going to be the difference between those two, and then the head loss for the third one is there. So once we've picked a head loss or a head for this value, we can very quickly get each of those losses, delta H. Once we have delta H, we can now use our Darcy-Weisbach equation here to quickly get a Q, assuming that we have a fully turbulent flow situation here, or that we know the friction factor. So on problems like this, when you're often going to assume the friction factor is not changing. So the best assumption for that is usually going to be that it's fully turbulent. We can go and get the friction factors for each one. But at the end of these problems, once we go through all the other steps, we should go back and really check the friction factors, and we might have to go through and do it again with the new values of the friction factor once we've kind of gotten to the end of the problem. But anyway, so for this, yeah, everything, once we've gotten delta H for each pipe, we can then get Q, and then we can check the closure. And the closure condition in this case is going to be flow in equals flow out. So in looking at the junction, this reservoir, as it's arranged here, this reservoir is clearly going to lead to flow going in because it's the highest elevation. This one is clearly going to have flow coming into the reservoir, so flow is going to be coming out of the reservoir and into the junction from this one. For this pipe, it's going to be coming out of the junction and into the reservoir. Pipe 2, it could be going either way. We don't know that in advance. So we have to generally make an assumption. And so if we assume it's going in, we'd say Q1 and Q2 has to equal to Q3. That would be our closure condition. So we're going to guess a value for H. We're going to go through and figure out the flows. Then we're going to see whether or not we get closure. And then we have to go back and move the value of H up or down until we get that closure to work out. So that's the basic idea. And so again, this is talking through the procedure. The easiest way to understand it is to do an actual example. And we're going to assume typically that the flow is fully turbulent. Then we only have to iterate for H. That's going to be the only thing that we need to find. But in reality, once we get to the very end of this problem and we figure out the right value for H, we need to go back and update F technically. So this is sort of thing that makes this problem much easier to do in Excel, but you can do it by hand also. So here's an example. We are given the 3 reservoirs. We're told that it's conveying water at 20 degrees. So we have nu is 10 to the minus 6th meters squared per second. I've been using this in all my videos. It doesn't really matter though. If it's something else, it's not going to make the problem harder. If it's something else, you just have to look it up. We're going to have G is equal to 9.81 meters per second squared because we are looking at metric units once again. And then down here we're given the information for each of these 3 pipes. So pipe 1, 2, and 3. Pipe 1, the reservoir elevation is 120 meters. The second one is at 110 meters, and the third one is at 80 meters. And so we're going to need to make an assumption here about the directions of flow. Again, for pipe 1, it's got to be going into the junction. Pipe 3, it's got to be going out. This one could go either way, and I'm going to assume that it's going in because it's pretty high also. It's only a little bit lower than this one, so that's what is actually going to end up being right. But if you happen to choose the other direction, it's fine. You just get a negative number in the end that you need to use. All right, so what else do we need to do here? So we need to get our friction factors for the fully turbulent case for each of these pipes. So we're told that they're all average concrete, which means that our epsilon value here in millimeters is going to be 0.36. And, this doesn't have to be, they don't have to be the same in all 3 pipes. It doesn't really make the problem any harder or easier if they're different. Just you have to make sure that you get them all right for the material that you're looking at. Epsilon over D then, our relative roughness for each of these. We have the diameter here, we have the roughness height there. That is going to be 0.0012, 0.0009, and 0.00072 for the 3 different pipes. And so then from here we can go in and get the friction factors. So we could go to the Moody chart if you wanted. I'm going to, in this one, just say we use F is equal to 2 log of 3.7 over E over D quantity to the negative 2 power. And I've got E over D for each of these, epsilon over D for each of these. I can plug it right in there and I can get my initial guesses for the friction factors. So, we might call that like F turbulent and write those in. I didn't leave myself enough room here, but we're going to have F1, we're going to assume is 0.0201. F2 is 0.0195, and then F3 is 0.0181. assuming fully turbulent. Okay, conditions. And I could have written them there if I'd left a little more room, but it doesn't really matter. So now I've got a guess for F1, 2, and 3. Again, assuming fully turbulent. So when we finish this problem, really we have to go back to the beginning and redo it all if it turns out that any of those pipes isn't in the fully turbulent regime. But it does turn out also that the numbers that we have will not change very much if after we do that. So it's the right approach here is to assume the friction factors aren't changing and then to make an adjustment to them at the end, and then you can do it all again. Again, not a big deal if you have a spreadsheet. Okay, so remember our procedure here is we need to make a guess for HJ. So we'll guess or assume, if you will, that HJ is equal to 100 meters is what I'm assuming at the beginning. The best guess is often actually that it's at the same height as this second reservoir, which would make the flow rate 0 and could save you a little bit of time. I'm just going to assume it's 100 here. But if you want to know what the smartest guess is, you'd generally like to be smart. Then assuming that it is the same as the second one is going to be usually the fastest way to get to the right answer. Okay, so we've got our H1. So now I'm going to go to the next page. So delta H1 is going to have to be equal to 20 meters. So if I assume this is 100, then the difference across this pipe, remember, head is at a point, it's like a state variable. Head loss happens across a distance. It's related with the pipes. So key idea, this is an important thing you have to keep in mind conceptually. So this is 100, head loss is 20 here, 10 here, and then 20 here. Okay, delta H1 is 20, delta H2 is 10, and delta H3 is 20. Okay, and now I can get Q1 is equal to pi squared G delta H d1 to the 5th over 8L F1, and that whole thing's square rooted. Let's see. Yeah, and so this is our Darcy-Weisbach equation, and again I can kind of group all this together except for the delta H. I could leave the friction out if I wanted to. So pi squared G d1 to the 5th over 8L. Yeah. Delta H1 over F1. And so pi squared times 9.81 times d1 is 0.3 to the 5th over 8 times 1,000. All that to the half. Delta H1 over F1 square rooted. And so we're going to use this term over and over again. So I'm just going to, in the interest of time, you might want to calculate it. Okay. So this isn't going to change even if the friction factor and delta H changes. And so then we're going to have to do this again and again to get it right. So it's kind of convenient to save the time of having to do that part of the calculation every time by just coming up with a number. So 0.00542 times 20, and then we had F1 was 0.0201 square rooted, and that gives me 0.171, and the units are going to be meters cubed per second. All these are in, I wrote everything in meters, so, and we have seconds in there, no other units, so we don't have to bother, but you have to make sure the units work out if you do have different ones. So, okay, Q1, Q2 likewise is going to be pi squared g d2 to the fifth over 8 L2, this is 1, square rooted times delta H2 over F2. And so if I plug all those numbers in for Q2, I get 0.00787 times delta H2 over F2. And our delta H here is 10, and our F2 is 0.0195 square rooted, and so that gives me 0.178 meters cubed per second. Q3 likewise with D3 and L3, I'm going to get a number here, and that is going to be 0.0138 times delta H3 over F3 square rooted. And so that comes out to be 0.0138 times 20 over 0.0181. Comes out to be 0.459 cubic meters per second. All right, so now we've gotten, for the initial value we guessed for Hj, we followed that through and said that these are the three flow rates that have to come out of that if that is right. And so now we need to check the closure, and so we have Qn is equal to Q1 plus Q2, and if I add those two together I get 0.349, and then we have Q out is equal to 0.459, only this one is coming out. So Q out is bigger than Q in, or Q in is less than Q out. Q in less than Q out. So what does that mean? That we're not getting enough flow coming in, and we've got too much coming out. So we can get more flow coming in if I were to lower this down, then the Q's would be bigger here, and then I'd have less head over here to push the flow out here to 80. So that means that this is too high. So Hj is too high. Too high. Yeah. So I might now guess that Hj is 98 meters, and if I do that, then my delta H1, if I say this is 98, then we've got 22 here for delta H1, 12 for delta H2, and 18 for delta H3. 22, 12, and 18. And so I can then go in and, you know, again, I'm not going to update, I'm not going to try to update my friction factor. I could at this point go through and find the velocity and update the friction factors. I didn't do that at this point. Generally, it's better to just iterate through and get the head and then worry about the friction factors at the end. But you could do that. But so assuming the friction factors are the same, then I get Q1 from this exact same equation right up here. I can plug everything in. I just need to update my 20 to a 22 and so on. Then I'm going to get Q1 is equal to 0.179. Q2 is 0.195. And Q3 is 0.434. And if I look at the closure here, these still add together to be less than that one. So Q in less than Q out still too high. So I go down to 96. If I assume Hj is equal to 96, I'm going to get Q1 is, let's see, 0.188, Q2 is 0.211, and Q3 is 0.405. And this is getting to be pretty close. You know, still too high, but close. And so then when I went to 95.5, I got the Q1 was 0.19, Q2 is 0.215, and Q3 is 0.405. Let's see. Yeah, and so this ends up basically closing. So closure. At this point, then we would need to get the velocities to get the friction factors. So now check Reynolds. So we get V1 is Q over A1, which is Q over pi over 4d squared. I'm not going to write all that out. Hopefully at this point you've gotten that figured out. So V1 is 2.69 meters per second, V2 1.71 meters per second, and V3 is 2.06 meters per second. Reynolds number for the first one then, again, is dV over nu, same as we've done before, nothing different here. 8 times 10 to the 5th, Reynolds 2, Reynolds 3, 7 times 10 to the 5th, and then 10 to the 6th. So, you know, if we were to go look at our Moody chart here, or if we were to plug those numbers in to the Swamy-Jain equation or another equation to estimate the friction factor here. So if we look at the smallest one, 7 times 10 to the 5th, and F2 is 0.019, or sorry, E over D2 is 0.0009, so 0.0009. So it's kind of like between these two, right? Yes, it's almost 0.001. So it's right in there at just under 10 to the 6th. So if we look here, you know, basically we are still at the fully turbulent regime. I mean, it is technically on the left side of the line. And so you might want to update it and then redo all this again. But so at this point, you could go through and get each of the 3 friction factors, and then you could go back with this same value of Hj and get your new Qs. It would change not very much. I don't even know if it would change here at the level of the significant figures we're looking at. But technically, you would want to do that to get this all to close mathematically. You know, if you're doing it in a spreadsheet, it's not a big deal to build something like that in. But so these are basically close enough. But so this is how you analyze a pipe junction. The really important idea here, so again, you're not going to see 3 reservoirs connected like this in the real world. The key idea here, though, is that we might have a junction here, we might have a junction here, and we might have another junction here. And the way that we're going to analyze this junction is by looking at the head difference between those 2 junctions, these 2 junctions, these 2, okay, and making sure that we have the mass that flows in has to be equal to the mass that flows out, and we also have to make sure that our Darcy-Weisbach equation, or whatever energy equation we use for each of those pipes, is obeyed. And then in a real system, you'd have more than these reservoirs, so you'd have to, you know, you'd have to set this up for every single node that you're looking at. So we'll talk about how you can do that briefly in the next video.